Good afternoon, everyone. Hi, I'm Chetan Venkatesh, your leader for the revolution this afternoon. Thank you very much for making it my session. I realize that I'm the man holding you back from the beers, so I will try to be as concise as possible, although that candidly is not one of my strengths. And therefore, I would request if you have questions, just pop your hands up. If you have comments, pop your hands up, make them, ask them, because there's not going to be any time for Q&A at the end, and I certainly want to get a couple of drinks down. I've been working on this presentation all day. Having said that, in my alter ego world, I'm the CTO and founder of a company called Atlantis Computing, which focuses on providing a special type of software that enables storage to really go in a turbo mode, that really accelerates storage and allows you to build very large-scale virtualization, VDI in particular. And my product is used globally by all the Fortune 100, Fortune 500 type customers. We've been deployed in large banks. We've been deployed in healthcare, et cetera. We work with VMware and Citrix. I think there's a rule in BriForum that you cannot shill for your company, so that technically is not shilling. I'm just telling you about myself. But this is a topic that is really close to my heart. This is my fourth BriForum, by the way. So yay for me. And by the way, this is the best looking crowd I've managed to get in a session so far, so yay to you. So, for 4 years now, I've been trying to do this, trying to build an end-to-end soup to nuts VDI infrastructure using just open source tools and technologies. And I think I'm really that close this time around, because for 4 years, I've been tracking different projects. I've been getting all kinds of code. I've been sitting and hacking bits up, trying to put it all together and make it work. And the intention really is to make something that's more than a little bit of a toy that actually can be put to work for users. And so this has been a great experiment, a great joy to learn over the last 4 years. So I've started to condense everything that I've learned in the last 4 years into about 200 odd slides. And hopefully we'll get through all of them this afternoon. Shane, Mark, how are you? It's great to see you again. So without further ado, let me launch into sticking it to the man, building a production VDI with free and open source technology. So, what's a revolution without a little social networking? There are several precedents, Iraq, Libya, et cetera, et cetera. So if you're going to, I would highly encourage you to tweet about the session. If you're going to tweet about it, please include hashtag BriForum -- stick it to the man, STIM in there. Tweet me at Chetan if you have feedback, comments, brickbats, anything that you have. Also, this presentation is completely open source, and I'm going to make it available on my website, sometime this week, and you can download it. And I also plan to take everything that is a part of this project and make it available for download, sort of a one place repository for you to get all this information. Couple of caveats. This is not going to be slick. There's a saying, when you make sausages, you're going to get bloody. And this really is all the gore of the sausage making process. This is a deeply technical session, and I know it's 4 o'clock in the afternoon, but you guys have the mental wherewithal. I believe in you. And there are lots of open questions, so I don't have all the answers either. So you might ask me questions and completely stump me. I'm still very brilliant, by the way. But if that happens, it's okay, So in agenda in no particular order, and I really mean no particular order because we can flip back and forth, we're going to talk about VDI a little bit, not too much, because everyone's sick to death of hearing about VDI and how it never shows up, and it's the proverbial next year's technology. And Brian's even made a few $1 million writing a book about it, which were all bought by Quest, I hear, who eventually sold to Dell. I wonder why. Probably all those books they bought. But VDI is something that we need to revisit in the context of open source. After that, I want to talk a little bit about the open source conundrum itself. This open source stuff is not easy. How many of you people have dabbled in open source? And how many of you have attempted virtualization with open source technologies? So that's a subset of what we talked about. And how many people have actually attempted VDI with open source components, not necessarily soup to nuts? Well, we got a half a hand over there, so I guess that really does make me the expert over here. I feel much better. So we're going to talk about the open source conundrum, what it actually involves to try and put these kinds of projects together. We'll talk about the anatomy of an open source stack for VDI. In particular, I want to talk in this order: the storage platform, hypervisor, the Windows layer, and the thin client platform. I'm going to try to be as broad as possible because there are so many pieces to the stack, and that's why VDI is so hard to understand and operationalize. But storage I necessarily started with because it's the hardest part of VDI. It's the most expensive part of VDI, and it's the part that kills VDI. And for long and hard, I've been looking for a storage technology that could actually be a practical solution for VDI. And I think I have some answers today, and I'd be very curious to get your feedback on that. After that, we're going to actually put it all together, all these different pieces, and see what this architecture looks like, and maybe we'll have some time for some questions after that. But again, encourage you to to ask questions during the session, make comments. Let's keep it interactive. So, VDI ahead. Warning, we're going to talk a lot about VDI, and in BriForum, VDI is some sort of a bad word in some ways, because enormous amounts of speaker time and PowerPoint is spent on bashing VDI, etc. And it breaks my heart because there are 3 VDI myths that I really want to tackle head on at the start of my session. The first myth is that VDI is some form of a venereal disease that is transmitted from person to person through sexual contact. This is not true. Number 2, VDI is not transmitted through toilet seats either. It's really not that kind of a thing. And there is this rumor going around that VDI is the love child of a VMware engineer and Microsoft Bob. I don't know how many people know Microsoft Bob, but if you know Microsoft Bob, raise your hand. All right, that's the bunch of people who are really old school over here, so yay for you. And the source of all these myths happens to be none other than this book by Brian Madden and Gabe Knut. And you don't get this if you just read it. What you have to do is get the audio tape and play it backwards. Get the LP, play it backwards, and every chapter starts with this sort of a preamble. That's my obligatory Reddit-style meme because I'm a cool open sourcer. But VDI really has taken a lot of contortions because people don't understand what it's for. It is a transformative technology. It is something that is in many ways a technology that will evolve at a glacial pace, but like a glacier will carve out an entire geology in the marketplace over time. And that's why we all get frustrated, because we all think it's something that you just install and off you go, but it isn't. And we'll talk a little bit about why it's that way as well. So these are VDI realities, though. VDI is complex, VDI is expensive, and VDI is politics. And I've been fortunate or unfortunate, depending on how you look at it, to be involved in some of the largest VDI deployments in the last 4 or 5 years. And if I can boil my lessons down to 3 things, it's really these 3 things. VDI is extremely complex. Windows, on the other hand, is a fairly simple animal because it was designed to run on a physical endpoint. And what we're doing is the antithesis of what it was designed for, which is taking it completely, wrapping it up in a layer of lies and sticking it in a very expensive piece of real estate called a data center, where people who generally make things very complicated live and breathe. So therefore, VDI is extremely complex because it's running in an environment which breeds complexity, which is supposed to run all the time, and therefore, as a necessity, requires a lot of complex technology and process and cone-shaped people to work there. VDI is expensive, and again, because VDI is in the data center, let's just accept it. There's no way to make things cheaper because the data center is an extremely expensive place, and there's a simple reason for that. Data center was meant to keep your data safe, and safety is very, very expensive. And when you keep data safe, you have to fundamentally work against the universe, because the universe is something called entropy, which is basically all about randomizing information. And as a result of that, you need to make multiple copies of your data. That's the simplest, most obvious way to fight entropy. In fact, biologically, we're all doing it all the time. If you look at our DNA, we've got multiple copies of everything. It's mostly redundant. The entire DNA, about 3% of it actually is useful. 97% is just redundant stuff. So to fight entropy, we build storage systems that are extremely redundant. And redundancy means spare capacity, copies of stuff, and stuff lying around idle, et cetera. And all of that adds up, and it becomes very, very expensive. Thirdly, and my favorite topic, VDI is politics, and that's probably what kills VDI a lot. You know, as desktop administrators, we were pretty happy until this thing came along. But it forced us to start working with two sets of people that most desktop guys detest. It forces you to work with server people, actually three sets of people: server people, networking people, and storage people. And so when you put these four sets of people together, it's very hard to agree on who's in charge, because the server guys believe VDI is their baby. Storage guys believe that VDI is in some ways their baby, because what is a VMDK? It's a file. It sits on a LUN. It should be my baby, right? The networking guys, of course, own the data center. They plumbed it together, so they feel it's their baby. And of course, at the end of the day, the desktop guys are the guys who are actually going to build and run this thing, and are going to be held up by the collar when the thing doesn't work. So of course, logically to them, it's their baby. So there's a lot of this politics that goes on in VDI, and it's very, very hard to actually make VDI work, because this politics exacerbates the expensiveness and it adds a lot of complexity to the whole thing. The good thing about open source is, it has all of these, except you can sort of just build it in your home lab and then show it to your friends and see, I did it. And so I like that approach, and that approach seems to have worked well. But the truth is, VDI does work. In 2012, we're now at a point in time where there is sufficient data and deployments in production at sizable scales that we know there are people who know how to make it work. We know that there are technologies available that can be put together and made to work. And there are numerous examples. Large global bank, one of my customers actually, about 80,000 desktops, one-third of their global desktops in the world use VDI, and they're in the process of transforming the other two-thirds over the course of the next 12 months. It took them 6 or 7 years to get there, by the way. They didn't get there in 1 year. 6 or 7 years of very iterative working with vendors, et cetera. Large Japanese financial services company, VMware's biggest reference account, 200,000 VDI desktops in production. It works. I've actually seen it working. And if you look at the last year alone, VDI deployments have grown up by 10-fold. And there's a lot of money in VDI. And Brian Madden and I did this talk 2 years in a row about why VDI is important and why it will eventually become the mainstream form of desktop delivery. Fairly controversial statements, but in many ways, all the things that we predicted are sort of happening, largely led by the consumerization of IT, all the stuff that Brian and Gabe like to talk about. But this is the most telling thing. VDI is among the top 3 initiatives for any Fortune 500 CIO. And that means that it's going to trickle down over the next few years, and it's going to trickle into SMB, it's going to trickle into service provider, and everybody's got to have VDI. But finally, I think we've got all the pieces of VDI figured out, all the bits and bobs from one end to the other end, and they're mostly complete and mostly mature, and you can actually scale across thousands of desktops across your entire enterprise. And that leads to an opportunity with open source VDI. Because if you think about open source rarely, and cloud is the exception, open source rarely has had fundamental innovation. Open source has been great at taking knowledge that was locked up in proprietary minds of engineers working for corporations and building analog products of that and commoditizing that knowledge. But on the cloud, it's taken a different frontier. I won't talk about cloud, but in general, open source has been like that. It's a follow-on, it's a follow-me movement. It takes great ideas that are locked up in patents, et cetera, and finds out how to unleash that for you. And I'm very excited about VDI because we can finally get to the point where almost every part of that stack is available in some component form for us to commoditize using open source. And that's pretty exciting because if you think about it, there's the potential to actually build a soup to nuts open source distribution that does VDI, and commercially supported by an open source vendor, maybe like Red Hat. And there's lots of money to be made. But more interestingly, there's a lot of pressure you can put on vendors with that kind of commoditization of technology that will just amp up the innovation and accelerate the innovation cycle with these technologies. I like this also because it's a great way to learn technology. Truthfully, this shit is really hard. 4 years, and it's in the last year that I've really spent time in my lab cobbling things together, and I'll tell you the kind of things that I had to do, but it's extremely hard. It's not for the average administrator. You really need to have a fundamentally good understanding of operating system, application, Windows, Unix, and hypervisor, and protocol, and WAN, and storage, etc. To really start to cobble these things together. So there's a fairly long wish list. I thought this was a great way for me to learn computer science. I have a bachelor's degree in computer science, academic understanding, but when I started to attempt this project along with my company, along with what I do in my company, that's when I truly started to understand the heart and nuts and bolts of computer science. So it's a great way to learn technology. It's CapEx friendly, in that it's cheap. If you can build some serious VDI infrastructure with very commodity infrastructure. However, you have to pay the piper somewhere. And if you're going to do it CapEx friendly, guess where you're going to spend all your money? You're going to spend it on your time. And we'll talk about how much of time goes in to make all of this work. So, you have to pay the piper somewhere. With commercial software, all of that is already packaged up for you, all that learning, etc., so that you don't waste your time with it. But with this, if you've got oodles of time, you've got spare time, you've got the motivation to learn, go for it. It's a great way to learn. And with a lot of love, care, good luck, you can actually get it right and get it to scale to thousands of users with time, patience, and effort. I've got it to scale to 500 users, and I'm pretty happy at this point. So I'll talk about that design, the 500 user design. So I talked about this. This is not easy stuff. It's hard, and here's why. These are the set of skills that I needed just to be able to get the infrastructure going. And this, by the way, is biased because I am a Linux man. I learned Linux first. I am very biased towards the way Linux was developed, etc. So it's very heavily skewed towards Linux. There are alternatives. You could use Solaris to do this. You could use ZFS. You could even use Windows probably, right? But because I'm so skewed towards Linux, these are the sort of things that I had to learn to get there. You need to develop some serious Linux chops. So if you're at the level where you're just doing ls, pwd, and you think you're pretty good at Linux, don't try this. You need to know a little bit of C, C++, and that, by the way, is a good idea regardless. Because you'll get a lot of code that doesn't work. And you'll need to go open it up in an editor. You'll have to VI it or Emacs it, depending on whether you're on the left, the right, you're Republican or not. But you'll have to open it up, and you'll have to go understand how this code works, read somebody else's undocumented code, and fix it. Post questions to or send emails to that particular author who will not reply for weeks or months because he's got a real job, and so on and so forth. So you got to have some coding skills. The coding is easy. There's this thing called make, which is a terror. And that's actually getting the shit to compile. So becoming skilled at make is really good. If you can get good at make, you'll make your life a lot easier. And everything is written in somebody's favorite language, and people are not adequately satisfied with the number of languages that there are, so they invent new ones, and then they write their code in those languages. So you actually have to learn a variety of languages. It's good because at a point, you start to see all the generalities and the similarities. So every language basically is nothing but a variation of another. I particularly hate Python because of that stupid indentation structure that they have. I wanted to get that out of my system, so I'm telling you right now. This bit is also something that I think is mandatory. Understanding the internals of Linux. And I mean the kernel. And this thing is a work of art. Truly, it's one of the treasures of mankind. When you start to study the Linux kernel, you really start to appreciate and understand what a computer is, and how a computer's evolved, and how computers, different types of computers, are different. From mobile devices to PCs to servers to supercomputers, etc. You start to get an appreciation for all the complexities that are in over there. And there's so many projects. If you go to SourceForge, or if you go to Google Code and you type in storage file system, you will get about 400 results. And probably 350 of them have some source code attached to them. And there's some very valuable ideas in probably 300 of those projects. And about one of those projects might work. So you've got your work cut out because you've got to go and dice all this stuff together, splice it together, understand it, make it work. So this is how it looks when you deploy VDI commercially. If you just go to VMware or Citrix or Dell or whoever, I sort of made this up, but I think it's fairly reasonable. This is how your time is spent. 10% of your time is spent installing, another 10% configuring, 5% debugging, 10% rolling out, and then you go into operations mode, you roll the stuff out, and it's steady state at that point. Of course, during all this process, once in a while you stumble upon a problem that really kicks your ass, and you spend some hairy amounts of time doing some yak shaving. And that's about 5%, And that's why there's a lot of documentation on blogs about VMware and Citrix, because there's very little yak shaving, and anyone who does it can put up a little blog and share that information. But if you look at open source, it kind of looks like this. You spend about 45% of your time yak shaving. And there's just too many yaks to shave, so who's got the time to sit and write about all this stuff? And that's one of the reasons why there's so little documentation, because everyone, by the time they get this stuff to work, they're too tired, and their wives are cranky, and they need to go back and take care of their families. But if you look at how this time gets spent, about 5% of it is spent installing, because people write good documentation for the installers. They tell you, steps to install, 1, 2, 3, 4, 5, you're done. But it won't work. So you need to configure it, and you spend about 20% of your time sitting and configuring all this stuff. Even after you configure it, it basically does not go beyond whatever the equivalent of the hello world function is to actually make it really work. You need to debug it, you need to hack code, you need to compile it, et cetera, et cetera. So you spend another 20% over there. Rolling out is easy because there's so much of automation written into Linux today. There's so many different platforms available for you to roll out, auto-deploy, self-tune, et cetera, et cetera. So rolling out is a piece of cake. Operations is about 10% because you'll have, you'll have whatever small base of users, but yak shaving, that's where you spend all your time, crunching through problems. So it sort of makes you a marathon man when it comes to code and when it comes to technology. So having made the mandatory, disclaimers, and hopefully have scared some of you into not attempting this at this point, let's talk about some of the goals of this particular session. So we want to build a production-grade VDI. We don't want to build a Mickey Mouse, little toy. We want to build something that can actually be deployed for your end users, and hopefully you don't get fired by doing this. We're going to use free and open source technologies as much as possible, except for Windows. Obviously it's not open source. Although there is a very cool project called ReactOS, which is trying to build a completely open source binary equivalent of Windows XP. Why Windows XP? Because it takes them that long to reverse engineer stuff. So you get why this is such a hard job. I want to provide a reasonably detailed architecture, soup to nuts, for 500 users. I'm very enamored by this cool little thing called Nutanix. It's a nice little architecture. I want to give you something that's kind of like Nutanix. So you don't have to buy a SAN. You don't have to buy a NAS. It is basically compute and storage all in one box. And you can do that with a Supermicro or with a Dell or whatever. It's a software, really, that drives this stuff. So I want to give you those ideas. I'm sure that I'll be really popular with the Nutanix guys after this session. I will provide a website where you can download all the stuff. And it's my goal at some point, if eventually, to actually package all of this up into a distribution and make that available and have a one-click install, et cetera, et cetera. So I'll get around to that in about 15 years. So let's talk about the anatomy of VDI. These are all the different pieces that are required to be pieced together realistically for VDI. And you can get fairly anally retentive and say, well, there's more, there's this, there's that. But broadly, these are really the pieces that you require. You need storage, because you've got to store those VMs somewhere. They've got to run somewhere. You need network to connect the VMs to the thin client. You need network to connect the storage to the servers. You need network to connect the servers to the server. No brainer. You need a hypervisor because this is a virtualized environment. You're going to need some form of a connection broker. Well, there are some caveats we need to make over there. You can do persistent desktops, one-to-one named relationship desktops by giving users a hard-coded IP address. And that's how they did it in the beginning, and that might work for some. But ideally, you want to be able to go to some sort of a little portal and connect to a session without being exposed to all the internal mechanisms. And then, of course, you need Windows on top of all of this. And it's not as simple as just dropping Windows in and having it work. You'll also need to work with that image. You'll need to figure out how to create 500 images. You'll have to figure out how to customize them, join them to 80, all of that stuff. And there's this little thing called app virtualization, which helps you simplify some of these aspects as well. So it'd be cool if there's some way to do some of that app virtualization, share a common package, a payload of applications among multiple images from a network drive, for example. So we'll explore that. You need some form of thin client enablement. And I like repurposed PCs and laptops, et cetera. And so we'll look at a platform that allows you to repurpose existing PCs, et cetera, using open source to act as RDP and ICA thin clients. And finally, WAN optimization. Because a lot of the stuff is accessed over the WAN. And I was actually surprised. There is a lot of component technology in the open source world that can be used for WAN acceleration. Think about that. You pay thousands or millions of dollars for WAN acceleration, and potentially there are solutions for even that in the open source world. However, given that we've got only 45 minutes, these are the things I'll talk about. And this is how hard or easy it is to do. The more stars there are, the harder it is to do. Storage, damn hard. Hypervisor, fairly easy. Windows and app virtualization, damn hard using open source, because open source people hate Microsoft. And the thin client platform, probably the easiest of them all, because it's such a mature project. So these are all the pieces that we'll talk about today. So quick design goals. Must be practical to deploy. That means it's got to be cost effective. It can't be something silly. It cannot be Joe Tucci rich. It's got to be something that an average budget for an average IT department can support. It's got to perform within expectations. Now, you get what you pay for, so keep that in mind. You're not going to get something that's a rocket ship over here. It's not going to be flash cache and whiz bang. It's going to work at an adequate speed. It might be a good replacement for your aging XP desktop estate. It's got to have each part of that stack has got to have equivalent analogs. So if there's a broker in the physical, in the commercial world, we're going to talk about a broker in the open source world, et cetera. And by the way, I've taken the liberty of stretching the definitions of what broker means, for example, because sometimes those things don't exist in the open source world. And also from a practical operationalization standpoint, you're going to need high availability if you're going to do persistent desktops. You've got to have your VMs be available. I mean, it doesn't make any sense if your user is hosed if that server goes down, if the storage system goes down. So it's got to have the ability to do HA. And you need to be able to do some of the things that we take for granted in the storage world today, like thin provisioning, cloning, link clones, et cetera, if you're doing non-persistent provisioning, non-persistent desktops. And finally, it's a nice to have, and we'll attempt this, a pod-like architecture like a vBlock, which is completely open source and free. Something like the Nutanix, actually, more than a pod-like architecture. So let's start with the most difficult, troublesome topic and my personal favorite, storage. In a simple nutshell, you need storage because you have VMs that are virtualizing their hard drives, and those hard drives are files that need to be placed on some form of storage device. And that storage, very importantly, needs to be consistent. That means when you write to it, whatever you read back has to be exactly what you wrote to it. It cannot garble the bits. It cannot play games with you. It has to be absolutely 100% consistent. And I'm making these points because it might seem really, really redundant, but these are the fundamentals of storage computer science. So we'll talk more in detail about this at a mathematical level. But it's got to be consistent. It's got to be highly available, which means that I've got to be able to read and write from that storage whenever I want, whatever time I want, however long I want. And it's got to have adequate performance and enough IOPS. Now, IOPS is this weird term that probably most people hadn't heard of till about 2 or 3 years back. And now suddenly it's the forefront of VDI. And we'll talk about IOPS because IOPS is a very, very big deal. You see, because fundamentally what we've done with Windows and VDI virtualization is something very stupid. We've taken a Windows PC, which for the last 20 years Microsoft has assumed has a local drive and a local processor and some local memory, right? And they've written this operating system to be highly interactive so that when you click on start, launch Microsoft Word, it happens very, very snappily. And so that architecture assumes that there's a local drive involved. And what are we doing with virtualization? We're breaking that exact assumption and taking that hard drive, virtualizing it, and sticking it on something that's shared. Now, shared means contention, as you would know from any kind of a lunch buffet table. When there are more people than there is enough food, there's a lot of crowding that happens, and everybody slows down. And that's basically the problem when it comes to virtualization and storage. Windows exacerbates this problem tremendously. And we'll talk about that. But before that, I want to address the requirements of storage in the context of VDI. There's a very famous theorem called Brewer's theorem, which talks about data and networking. It talks about how database applications behave. And it can be extended to storage with some restrictions. But fundamentally, Brewer nailed it. He said between consistency of data, availability of data, and performance, you can only pick any two at any given point in time. And that is a real problem, because ideally you really want all three. It doesn't work for you if you only have consistent but highly performant data that is very irregularly available. Or on the other hand, it's highly available, very performant, but is not consistent because you're going to have lots of blue screens. So what has happened in the storage world is that almost every storage system has been optimized for consistency and availability at the cost of performance. And that's why you pay so much money for storage when you start to deploy virtualization, because you need faster storage, but that storage is not designed for this. Our storage in the data center is from a mainframe era, where data needed to be highly transactional, highly available, and stored for long periods of time with a great deal of safety. And what we're doing is we're taking that very expensive, highly reliable storage and putting Windows VMs on them, and then Windows does all sorts of ugly things to that storage. We'll talk about those ugly things. But that's what we're doing, and that does not make sense. And so one of the things we'll attempt in this VDI architecture is to skew this away from using that class of storage to using commodity storage. And Windows is a crazy workload. It's very, very different from server virtualization. I'll talk a little bit about why and how. Servers are fairly well-behaved workloads in most cases. Servers are typically headless applications. There's a database, a web server, and some sort of an application tier that sits in between. And for the most part, you can very easily predict what your high watermark of utilization and what your low watermark of utilization is. And from a storage perspective, servers spend a great deal of time reading rather than writing. Most server applications do. I'll give you an example. I was trying to fly to Chicago and needed to book a ticket, went to Expedia, spent 20 minutes on Expedia's site, just running different searches. What was it doing? It was reading some storage again and again and again. Finally, found what I wanted, filled in a form, hit submit, paid my credit card, and that's the only time it actually wrote to storage. So if you look at the overall I/O workload pattern, it was 99% read, 1% write, right? And that's easy. And so storage systems have been really driven and optimized for that. So you have all kinds of cool technology for caching, all kinds of algorithmic prediction algorithms that figure out what you're trying to read, bring that in before into the cache, and make the storage as fast as possible. But Windows desktop is a completely different animal, because Windows is not read intensive, it's the opposite, it's write intensive. And here's why. A Windows desktop is an interactive workload, which means that it has to always provide, what do you call that word? It has to provide a response time as quickly as possible. Instant gratification, let me put it that way. The more time it takes between you clicking and being gratified by the launch of an application, making something go away, etc., the more irritated and annoyed you get. And so therefore, the whole operating system has been tuned, believe it or not, yes, it has, to drive that interactivity, okay? And that basically means it changes the way it deals with storage. So that's one problem, that interactivity. So what it does is it actually prioritizes read requests versus write requests. It's always trying to issue read requests and get them serviced first, because every time you click on anything in Windows, start menu, launch application, it's got to read data. But the second problem is a far bigger problem. In a server workload, you run a very small set of defined applications. You don't take your database server and run, some sort of a weird web application on it. It's a database server. And so there's a very deterministic memory model. It takes memory in some very predictable forms. That's because you know what it is, and you can size it for that. But in a Windows desktop, like the one you have on your computer, like Jim has over there, you can launch any application at any given point in time. I could launch Word, I could launch Excel, I could launch Minesweeper, and then I could launch Outlook, and I could keep going on. And so that operating system has to deal with a lot of randomness and not enough predictability around what the user can do. So it has to make guarantees that it can launch and run your applications with the limited resources it has, not knowing what you'll do in the future. And so the programmers, and this is a 50-year-old, 60-year-old solution, programmers, what they did was they came up with a clever solution called virtual memory, which is the way the banking system kind of works on Wall Street, or it used to work in Greece, let me put it that way, which is basically, I'll tell you, you have the memory that you need, but I'll only give you this much. I'll sort of virtualize the memory completely, right? And it works well enough, because you might launch an application, it says I need 1 GB of memory, and the operating system says, here's a GB of memory, but actually it's only 100 MB, and it'll on demand give it as much as it needs. And if it finds any kind of memory that is inactive even for a few milliseconds, guess what it'll do? It'll take it and dump it to disk. Why? It wants to free up memory because you might launch another application that needs active memory. So virtual memory subsystems are a big part of a Windows desktop. And they do a lot of paging in this uncertain world to be able to cater to applications that can be launched at any given point in time. Couple that with this need to be very quick and instantly gratify the end user, and you have a workload that actually spends 70 to 80% of its time writing to the disk. And that, ladies and gentlemen, is why your computer disk keeps whirring around and the little light keeps going on even when you're doing nothing. End of session. Right? So that's a big deal, 80%. Now, also, most of the I/O that is written by the Windows desktop is small I/O, 4 kilobytes in size. Why? Because the Windows page size is 4 kilobytes. So it reads and writes in 4 kilobytes chunks all the time. As your disk gets more and more defragmented, all the stuff gets sprayed around the drive. There's a lot of latency in going and getting that, which is how a system degrades over time. It's not Windows. It's a lot to do with this interactivity problem, right? OS X has done some very clever things. OS X in particular has focused a lot on caching reads, doing interesting things with reads so that you can unblock the first problem from the second block. And they do a lot of different things around their virtual memory as well. Separate session for BriForum 2014, but I'll put a pin on it for now. Lastly, there's a lot of, in a VDI design, there's a big variance between peak usage and average usage. For example, if you take somebody's computer, run a little monitoring tool to see how much CPU they used over 1 week, you're basically setting yourself up for big failure because when he launches an application, it might burst to 80%, 85%, but then it sits idle while he's doing something that's not necessarily CPU intensive, he's gone for a coffee, et cetera, and so it normalizes the entire curve out. And the same thing happens with storage and I/O. A lot of people like to go out and look at the average IOPS requirement that a Windows desktop has, and different vendors have hazarded different guesses at it and have tried to sell storage around that. For example, a very well-known storage vendor that sells a NAS that rhymes with WhatApp basically said that you need 2 IOPS per desktop at one point in time. And then they revised that to 8 IOPS per desktop. But fundamentally, if you look at a PC, it has a hard drive that's a SAS drive that gives it about 150 IOPS. And therefore, that at the very least, you're going to need something in that ballpark to make this, any kind of an experience that is equivalent to a physical PC. So big challenges over there. So, when you start using shared storage, these things all become fairly big considerations. Now, this is the other layer of complexity and why Windows is so hard to virtualize, which is Windows was built for the physical world. It wasn't built for the virtual world. All virtualization is successful lying. And I want to give credit to Jim Moyle for saying that over a few beers the other day. I think it was a few months back. But all virtualization is successful lying. And with all lying, there is always a downside. And so when you lie to Windows and you tell it its CPU is virtual, it doesn't care. It seems to work fine. It believes it. When you tell it its memory is virtual, that works too. But when you tell it its disk is virtual, a lot of bad things happen. A couple of examples of what bad things happen. Number one, Windows still thinks it's running on a physical drive. And it has a lot of optimizations within the system to maximize the performance of that physical drive. So one of my favorite optimizations is something called sector latency optimization. What Windows does is it basically looks at at your hard drive, which is a set of concentric cylinders. And so the cylinders that are on the outer edge have a bigger radius and circumference, and so there's more data that can be read and written in one rotation, versus the ones that are in the middle or in the inside of the disk have a much smaller circumference, so very little data can be written there. So if you have data in the inside part of the disk, you need to move the disk head more to get more data out. So that means latency because you need to physically adjust the disk. So Windows has a beautiful optimization that works great on a physical PC that will move data from the inside to the outside all the time for popular data. So it keeps looking at what data is popular, where is it physically located on the disk, and pulls it out. And that works great on a physical PC. But what happens when that is a VMDK or a VHD? There is no inner circle, there is no outer circle, all the circumferences, all are virtual bullshit lies that are being told to the hypervisor, and as a result, Windows spends a significant amount of its time moving imaginary bits from an imaginary inner circle to an outer track, and spends a chunk of its I/O doing this. So there's all this fun kind of optimizations that come from length. This is just a bunch of examples over there. But by far, virtual memory is the biggest one. Virtual memory is the idea that you can do things, you can substitute a piece of real memory for disk and in an optimal way bring it back so that the user won't notice. But if you take the fastest kind of solid-state drive there is today, stick it into your machine, right, and see how much a page fault slows down your system, you'll be shocked. A page fault, even on the fastest kind of drive, slows your system down by 1,330 times, right? So you've got an application that's blazing. As this is a memory address, which is virtual, needs to go to disk, it just stops. 1,330 units of time, and then it starts again. And if it page faults again, so back and forth, back and forth, back and forth, this is what kills it. So virtual memory is the anathema of storage because centralized storage takes this virtual memory and moves it milliseconds away, physically, at the speed of light from where your application is running. So I want to eliminate these problems with this design as well. And some of my colleagues from Atlantis will be quite nervous because we actually have a product that does all this stuff as well. That was a Sublime shill over there, right there. But this is not addressing performance. Guys, relax. This is really about how to build an intelligent storage architecture for a VDI with open source. So I did an R&D project across about 100,000 desktops, various customers, to figure out where does Windows use all its IOPS, all the I/O performance that you give it. And here's what I found. About 35 to 40% is used by the virtual memory. About 10% of the time it spends moving imaginary bits from the inner track to the outer track. It does file layout optimization. You can't turn this stuff off. There are no registry keys, by the way, to turn these things off. And it spends another 10% if you have AV scanning, etc., I/O on that. Windows OS core, the operating system core itself takes about 15%, and that 15% is stuff that is meaningful to you as a user, saving your files, your registry keys, etc. So basically put, if you bought $1 million SAN, $850,000 of that SAN will be spent doing this gunk, and about $150,000 of that SAN will be spent doing meaningful things from an I/O perspective. Big, big waste of money. So Windows basically forces us to trade off performance for consistency and availability because without that, you really can't have a system. I'm interested in this design also to offset some of that performance. If you truly want to offset that performance, there are other ways to do it that are commercial, but I'm interested in a way to offset that performance. And that means don't use a SAN. Let's talk about that. So I try to build a SAN together to build my VDI, and this is sort of what I put together. I bought a 4U rack server chassis, dual redundant power supply. I put in a single socket dual core 2 gigahertz processor, 48 gigs of RAM, battery backed up RAID card, and I had 24 drive bays that I populated with 10K SAS drives, 300 GB each. Looks pretty good. 6.7 terabytes of raw capacity, yeah. If I put RAID 5.0, not RAID 5, but RAID 50, which is I split it into 2 groups of 12 drives each and put RAID 5 on each for better redundancy and some better performance because RAID 5, it kind of kills performance. I can get about 4.4 terabytes of usable space on this. Not too shabby, right? I lost about 35-40% of my capacity, but I got there. And so I can fit about 102 VMs on one of these babies, and I can put about 819 non-persistent link clone style VMs on one of these machines. But here's the problem. The usable IOPS capacity, because each drive has about 140, 150 IOPS, is only about 1,100 when you put the RAID penalties together and the fact that you've got a RAID 5.0 to offset some of those penalties. You don't get really a ton of 4K IOPS. You get better sequential IOPS, by the way. But these are random 4K IOPS that are mostly write and some read. But the average VM, and I'm toning this requirement down from 150 IOPS per VM to 30 because I think 30 is acceptable. 30 will work for the vast majority of users, right? You get only 36 VMs on a storage of this size. So if I wanted to build a production architecture for 500 VMs, I need to add about 333 more drives, or I need to add 13 more storage servers like this, because just adding drives won't help. I need storage processor, I need more RAM, et cetera, et cetera. And this fundamentally is the biggest problem. The IOPS will not let you use centralized SAN, centralized storage, to drive this effectively. So if you look at comparing what will, I like local disks because local disks are cheap and they're fast. So if you compare them across some of the parameters that are important from a virtualization standpoint, both are consistent. SAN has the advantage of being highly available. Local disk doesn't. If your disk dies, you're dead. There is an IOPS problem on both to a large extent, but local drives are slightly better. One is very cost-effective, local drive. The other is not. And then with a SAN, you get some higher-level features like snapshotting. You can do persistent VMs because of consistency and availability. And you can do non-persistent, which, by the way, local disk can do as well. But my ideal solution has yes in all columns, has yes across all the rows, and that's what I'm going to shoot for with this design. So how do you get a design that does centralized storage, that can also do high-level storage functions like snapshots and clones, is highly available, but using local disk? Any answers? Any hands? There is an amazing, amazing piece of technology in the open source world. It's got the world's stupidest name, but it's an amazing technology. It's called Sheepdog. And what Sheepdog does is it builds a clustered block storage device for you. And people have attempted clustering forever and ever. Clustering technologies have existed forever and ever. People have built clustered file systems, distributed file systems from Microsoft, et cetera, all do this clustering. However, when you do it at the file system level, there are a lot of inherent performance trade-offs you need to make for that consistency and availability. What Sheepdog instead does is two things. It focuses at the underlying block storage level and clusters at that level. But more importantly, it's only for virtual workloads. It's meant to basically store and distribute VMs. It does a shit job of doing anything else. And I love it. Because purpose-built storage, purpose-specific storage is the next generation of storage technology. For the last 30, 40 years, we've been building basically different ways of taking the same storage and presenting it different ways to the application. So we started with DAS. Then we took all the stuff that was not latency sensitive and put it on a NAS. And then we fully virtualized the storage solution and made it a SAN. So it looks like it's local, but it sits on the network. But that's all we've done. We've just moved the storage from there to here. But this is really the next generation of stuff. Content-aware storage, purpose-specific storage. This thing does VMs, and it does only VMs, and it does it really, really well. So distributed block-level storage runs on local storage, aggregates server nodes. So you basically have boxes of servers with local disks, install the stuff on it, point it to the storage, and it'll automatically take the storage that is available on that node and make it a part of a big pool. And it'll manage all of this stuff without you getting involved in it. And what is amazing is it scales and it scales and it scales. And I'll talk about that in a bit. But you can keep adding nodes and keep getting more capacity, but even more performance. You get capacity and performance at the same time. And it's got the set of features that are specifically meant to drive virtualization and VDI. Snapshots, cloning, thin provisioning, etc. So this is the find of the century as far as I'm concerned. Great little project. It's been around for about 3 years. It's still in, I would say it's in RC, release candidate stage. Put it in production at your own risk, but I've been running it for more than 7 months, haven't had a single outage. It works beautifully. And guess what? This thing, local disk with Sheepdog, gives me a yes in all those particular columns. It's a great piece of technology. So let's talk more about Sheepdog. So what Sheepdog does is very simple. You take a normal server, like a Dell 420, R410, R520, whatever, a Supermicro box, 4 drive bays, put in 4 10K SAS drives in them, put a RAID 0 on them. You know why? Because the redundancy is not provided by the hardware. The redundancy is provided by the software. You're doing things intelligently now. Okay, so you've got RAID 0, which means you get a lot more IOPS from those drives. Okay, one of those drives fails, your whole node is host, but that's okay. It's okay because we have this distributed storage device that will move those bits around and make them available somewhere else. And you have on top of that Linux, and in particular the KVM hypervisor, and Sheepdog installed into the KVM hypervisor itself. And what Sheepdog presents is a storage mount point into KVM on which all the VMs are available. And Sheepdog automatically manages the distribution and all those features. But let's just take a quick look at my pod. So my pod is basically a dual socket, quad core, 2 gigahertz or better. This box has to not just run storage, it also has to run VMs on it. So the Windows VMs will run on this box itself. Yeah, sorry, go ahead.
When we install the Linux, you take a drive and install Linux first and then present the drive?
Yeah, so in a simple fashion, when you get a RAID 0 volume, right? Put a partition, put an LVM partition, install your Linux on that, take the rest of the space and carve that out for Sheepdog. My preferred approach is to boot this thing also from SAN, so that you're using the node for nothing but just delivering VDI. Yeah. Good question though. Remember that this box has to run both VMs as well as the storage, so it's a little more beefy. It's got 64 gigs of RAM. It's got 4 10K SAS drives, and it's got 4 1 gig Ethernet ports. I take 3 of those ports and I LACP trunk them so that I can push more I/O between these boxes in the cluster, and I'll show you that in the next slide. So Linux 3.0 or better with KVM enabled. KVM has a fantastic feature called KSM, kernel shared memory, which allows you to deduplicate memory and pack more VMs on a single server. It's beautiful. So you can up the density of a VDI box by 25-30% using this particular feature. So I'm going to use that. And then I have Sheepdog with a special piece of software called CoroSync that does this distribution. And I've got Windows 7. I'm giving each Windows 7 2 gigs of memory. Actually, I'm lying. I'm going to overcommit memory slightly and use the KSM feature to deduplicate memory. So it's going to be a little more aggressive. I'm going to give each VM 1.75 gigs of memory, right? Put 4 VMs per core. That gives me about 32 VMs. And with that, that's my single node. That's one node in my cluster. 32 VMs, and it works like this. 32 VMs on one side, 32 VMs on the other side. Sheepdog automatically will replicate VMs for me. So as I create new VMs, as I install new VMs, as I power on new VMs on one node, all the underlying I/O and the changes to the virtual machine file are automatically distributed out by Sheepdog to the remaining nodes. It's configurable how many nodes that you want to replicate against. You can create a fault domain where you can have the ability to lose one node, the ability to lose 2 nodes, 3 nodes, 4 nodes, 5 nodes, so on and so forth. But the point is, it's very elastic. It allows you to design the storage infrastructure in a much more meaningful way than you could ever with centralized storage. And here's if you look at consistency availability, this is how Sheepdog handles it. Because it basically, so that little red box on the top left is one of the VMs and the data from that VM. It gets replicated to all the other nodes transparently, right? So if I were to lose one of those nodes, it's fine because I have redundancy at the block layer because those bits that belong to the VM are spread across the network. So as long as I have a minimum of 2 nodes, it's good enough to actually have complete consistency and availability. Any questions? Any comments?
So does it actually keep track of what is changing inside the VMDK or file, or does it just replicate all the time?
No, it's very smart object-based storage, and that's why it's VM object-based storage. So it uses an internal checksumming and copyright snapshot copy on write methodology. Every time a write is issued to a particular block, it knows where those blocks are distributed within the cluster, right? And it automatically sends a message. It sends a message, not the block, to the remaining cluster saying, invalidate that particular block. I've got a new copy of it. And it then transposes that across the network. So it's got very specific optimizations for driving virtual machines. And so it does that much better than any other system actually does.
So it's possible that you could be relying on node 1, but your read goes to node 3.
Yes. Exactly. And that's one of the benefits, actually. So that's a great point. He made the comment, is it possible that when you make a read request or on node 1, which is where your VM is running, that block is not available on node 1? Absolutely. That block is available potentially somewhere else. 99% of the time, it is available locally because it also has a local cache. Okay? But here's the benefit of being able to stripe your data across. You can basically read from it in parallel. You can write from it in parallel. So with every additional node that you add I/O capacity and I/O performance to the entire cluster. And that's a nice segue into my next part of this discussion, which is what's the performance of this thing. So you can add nodes dynamically, and that's what I like about this thing. So just configure another box exactly the same as the one that we talked about, plug it in the network, give it the IP address to the CoroSync to the Sheepdog manager, automatically adds it, automatically replicates it, starts to use it, and you can deploy your VMs on it. Couple this with KVM's vMotion capabilities. There's no equivalent of DRS in the open source world, but couple it with vMotion, and you have the ability to sort of load balance VMs across all of these nodes without really worrying about where the storage is and how it's mapped into that storage. It's pretty fantastic. So some quick performance benchmarks. This is a 3-node cluster. right? Three hosts with KVM and Sheepdog on it, running just one VM. So one VM has got its bits distributed over all these different nodes. And if you look at a 3-node, it's comparable to a FAS 2020 with 12 drives. It's not bad, okay? But here's where it starts to really excel. This is 64 hosts, 64 physical servers with 256 VMs running on them. And just start to look at how phenomenal this is. If you look at the little legend over there, the x-axis is the number of VMs that are participating, and the y-axis is the throughput as you add more and more hosts. So as you start to look at this, right, at about 8 nodes, you start to get the equivalent performance of a FAS 2020, right? But at 16 servers, it's about twice as fast as a FAS 2020. At 32 servers, 300 megabytes a second. At 64 servers, you're at the 500 megabytes a second range. You know, it just scales linearly by adding more and more nodes. And what I like about this particular solution is the fact that I don't really have an I/O problem at 30 IOPS with this solution because I can work with those boundaries with this type of a solution, and I can't do that with a SAN. So CAP now sort of semi-agrees. You know, you sort of get performance. I'll say sort of because there is no silver bullet. It's mathematically proven you can have 2 of the 3. And it is true. What you're doing, though, is you're sort of distributing the load and allowing aggregate capacity to compensate for whatever is locally not available. However, there is a trade-off. Can anyone guess what the trade-off is? Latency. Every time your I/O has to hop, your I/O slows down, and that takes a toll. But it's nowhere as bad as concentrating all of this I/O and sending it to a SAN or a NAS. Yep. Great. So SD features of interest, and this will be available. I don't have time to cover each of them, but this is where you start to miss Virtual Center because you've got to open up the command line and start typing these things. So if you want to create a VM, that's the command. If you want to boot a VM, that's the command. There's no right-click boot over there. If you want to create a snapshot, that's the command. If you want to manage Sheepdog at scale, you either write your own scripts, or you write your own code using a library called libvirt, or download OpenStack and use their alpha bindings. They're very, very raw, but they're kind of cool to play with. Where to get Sheepdog? Sheepdog is available if you Google Sheepdog KVM. And these are the requirements. It's fairly light on infrastructure, easy to set up in a lab and play with. I recommend you use Ubuntu or Debian. They're the simplest ways to start playing with Sheepdog because they have KVM available in them and you can start playing with them. If you're actually going to do this tonight, be sure to watch for the compiling of CoroSync. The libraries, when they just download, don't work, so you need to get the source and you need to recompile them as well. Yep. And if you have problems, it's usually very simple to troubleshoot. Go look at the CoroSync configuration file. It's usually, as always, DNS that's the problem. Make sure that they're resolving correctly to IP addresses. So a BOM with Sheepdog basically boils down to $200 per VM, and that is within striking distance of anything that's available commercially. And that's quite incredible. Each node gives you 600 IOPS, and that basically means with 18 raw IOPS per VM, and it's also got a local IO caching mode, which bumps up that by about 30-40% to about 24 IOPS. So I'm well within that striking distance of 30 IOPS, which is a meaningful place to be. Now imagine if you took those local drives out, SAS drives, and put in SSDs. You've got something that definitely gives you more than 30 IOPS. So for 500 VMs, I would need 15 nodes at 32 VMs per node. I'd need 2 nodes for standby, so about a total of 17 nodes. And that is far cheaper than that monstrous SAN box that we tried to figure out a couple of slides back. Moving on very quickly because we really don't have time. Hypervisors. Sheepdog only works on KVM. Very simple, so you use KVM because it doesn't work on anything else. Zen support is in the works. It's actually been written. You can download the Zen code and if you're brave enough, try and run it. VMware support is planned, although I don't know when. But incidentally, VMware has a very cool piece of technology coming out called CloudFS or something like that tries to do what Sheepdog does, but within vSphere. So look out for that in the next 6 months or 8 months. It's going to come out as some sort of an R&D fling first. I like KVM because it's super fast, offers many of the features that are available in commercial hypervisors for free, and it's damn fast. In fact, on some workloads, I've seen it actually be faster than even physical. How it does that is through some of the magic of software, KSM for one, and some of these other tricks. Kernel shared memory is a big deal because if you can allow memory to be deduplicated, then VMs can share objects in memory, and that's pretty cool. If I have an object in memory that is the same content as another VM that has the same content, why not just deduplicate it and use one copy rather than several copies? And KSM actually does that. And KSM is safe. It does not do this for page I/O because page I/O is, gets dirty and it slows down if you try to deduplicate it. So it doesn't do it for page I/O. Another feature that I like, hot plug of physical CPUs and physical PCI devices. That's really, really cool. And KVM gives you that today. Very good I/O stack. This thing was designed from the bottom up for performance. So they do I/O really, really well. They've got a high-performance SCSI disk pair virtualizer. They have ballooning. They have boot from SAN. They have VM migration. That, to me, is sort of the essential list of things that you need to have a meaningful hypervisor, and it has all of those pieces. Make sure that your that your server supports VT extensions. Otherwise, KVM won't work for you. And installation is dead simple. Relatively simple if you know Linux, if you know Zen, if you've done those things before, you've done VMware 2.0. This is really easy. If you're a virtual center jockey, you've never seen a command line, you're in trouble. Won't work. Most distributions ship with KVM today. So whether you get Debian, Ubuntu, SUSE, whatever it is, they already have KVM in them. Use them. I recommend either Ubuntu or CentOS. Those are very, very easy to work with. Takes about 30 minutes to install it manually, but there's something called Proxmox, which is fantastic. It allows you to script and automate all this installation, can do an automated installation for you, server by server, in parallel in 3 minutes flat. It's fantastic. So elastically, you can build your own little Amazon-like EC3 infrastructure for VDI that scales out and scales back in. Next, we'll move on to very quickly Windows. How do you get Windows into each of those virtual machines? And I'm a fan of unattended installers, and I was shocked about a year back to find something that is as capable as a commercial product called unattended. So use unattended to basically provision VMs with Windows. Set up a VM, edit it so that it can boot from, I'll actually walk you through it. This is what you'll need: a Windows CIF share, the unattended software. You need to configure DNS, and you'll need a Windows server to actually serve out all the bits for Windows. It's actually very simple. The point I want to take away is that it does everything that a RIS does for you, an RIS does for you. And it's completely free, it's open source, does all the cool things unattended that I've mentioned before. Even installs service packs for you, even installs hot patches for you, can even install applications. That's a little tricky though, because you need to open it up, change the configuration file, write your own scripts, etc. do it. But if you do it, it's a phenomenal tool. App virtualization. This is probably the weakest area in open source. There is no app virtualization. You have things that are sort of like app virtualization, and there's something called portable apps that allows you to sort of create these application modules that can be single-click run and installed and run at one shot. So they've taken popular applications like Firefox, WinZip, etc., and created these portable apps that you can take on a USB key. And that's the closest you have in the open source world to app virtualization. So, I would encourage you to go look at Portable Apps Launcher that allows you to take some of the more common apps, and I believe even Office to some level is supported now, and allows you to create a portable app that can then be deployed on a network share, and you can symlink it from your start file, from your start menu, etc., to launch applications, so you have a common base of applications. But on a scale of 1 to 10, this is a -5 in terms of maturity, in terms of robustness. It is absolutely deplorable and horrible. And it really is one of the weakest areas in open source. And, it's understandable. It's Windows. And people, open source people hate Windows. So that's why they don't pay any attention to it. User profiles. Again, just as bad as app virtualization. So just continue using whatever you're doing with Windows and Active Directory today. Don't try anything new. If you are brave, there is something called Script Start, which, by the way, only is free and open source if you're in education or a nonprofit or something like that. So I haven't documented in great detail, but that can handle user profiles for you. Finally, thin client platform, and this is probably where it's most robust. There's a project called the Linux Terminal Server Project, LTSP. It's been around for about 15 years. It's one of the most mature areas of Linux, and what it lets you do is build diskless workstations and diskless clients. And these diskless clients can boot from SAN with a very thin operating system of Linux and open up an RDP or an ICA console into your remote session. Very, very easy to install. In fact, I just made a little how-to on how to do this install. There's a live USB available. You can download it, burn it to your USB, stick it into your repurposed PC or notebook, boot from it. When it boots, it goes into a graphical user interface like the one over here. Go to Other, click LTSP Live, and you select the network interface, click OK, and it's done. And your whole laptop and PC has been repurposed as a thin client at this point. That's pretty incredible. So you can actually do thin clients using that. It gives you RDP and ICA. Final one, broker. There is no broker. So if you're expecting pooling functionality, the ability to have different lines of businesses and different pools with different policies associated with them, you better start coding because nothing exists. The closest that you have is a load balancer. Yeah, a load balancer. Something that was written to basically load balance web traffic. And this very cool guy called Kurt something, I can't remember his name, he actually sat and hacked it up to act as a VDI connection broker. So it does RDP connection brokering remarkably well in the sense that it'll basically load balance the RDP port. So one connection goes on the RDP port, it assigns it to the first VM. Second one comes in, assigns it to the second. So obviously this works for non-persistent, and you don't have to give out IP addresses to your end users. You can make a primitive connection broker, kind of where VMware View 4.1 was, I suppose, right now. Uncharitable, but that's okay. So, and it just works. There's also on this website a sample configuration file that works for VDI. So use that, it just works. It takes about 10 minutes to install. Obviously will not work for persistent desktops, so don't do it with persistent desktops. So putting it all together, this is my VDI architecture for 500 users using completely free and open source technology. It works. Unfortunately, I wasn't able to give a demo today of this thing. Many reasons, but I will make all of this available on my website so that you can test drive it, you can download it, play with it, and experiment with it. But that's the stack. The entire compute storage layer is compressed and becomes one using KVM and Sheepdog. And we use unattended Windows installation on top of that. We use portable apps for that. And on top of that is my infrastructure layer, which is composed of Windows, Active Directory, the Crossroads load balancer, the LTSP network server, which serves out to thin clients, RDP, ICA connections that connect into this storage compute nexus that runs underneath it. There's obviously many, many pieces that I haven't spoken about today, but that's what you get, 1 hour, 15 minutes. I could do a whole 4-day session, thing like BriForum, just talk about this stuff, and you will all leave exalted and thrilled. But unfortunately for today, this is it. I highly encourage you to come to my session next year, where we'll be talking about how to make low Earth orbital satellites that will deliver secure mobile telecommunications. And we'll use party balloons, chewing gums, BeagleBoard computers, string, tin cans, and lots of open source. I'll give you a sneak preview. It kind of looks like this. Ladies and gentlemen, thank you so much. It's been a real pleasure. Real pleasure. Thank you. If you have any questions, we've got a few minutes. We can take some questions and call it a day.
The Sheepdog, is it hardware agnostic pretty much, or like you buy a PC from Dell or a PC from HP?
No, Sheepdog depends. So the question was, is Sheepdog hardware agnostic, or does it depend on a particular flavor of hardware? Sheepdog depends on Linux and KVM. So anything that Linux and KVM will run on, Sheepdog will run on. Yeah, sure, go ahead.